I would like to ask the last presenter, Jinmei Zhao, from Gansu Agriculture University from China. Welcome. Okay, we see presentation. Please press full screen. Yes. Yes, perfect. But we don't hear. Please switch microphone.
We actually do not hear you. Try to switch on mic.
Jinmei, do you hear us? Yes, now I see you, but can you switch on microphone? No, it is too small. Full screen was correct, but we don't hear you.
Maybe you should write that in the chat. If Mrs. Zhao don't hear you, it doesn't help to ask.
No, we don't hear you. I tried to connect with Mrs. Zhao.
Can you hear me?
No, yes. Perfect. No, please, presentation.
弄不了，都说没有声音。
Everything was correct. Only share your presentation.
啥意思 ？Can you hear me?
真宇，你现在共享。
Yes, we hear you.
Can you hear me?
Yes,
Yes.
perfect.
Sorry. 嗯，
全屏。好了，可以了。
Perfect. We are listening.
good morning, everyone. It's a very great pleasure indeed for me to able to attend this meeting. My name is Zhao Jinmei. I'm a PhD candidate from Gansu Agricultural University. The topic of my presentation is comparison of my nutritional components and antioxidant activity of two large fruit categories of Cibaxin in Xinjiang of China. My presentation will be introduced from the following 5 aspects. First, background. 状元黄 and 深秋红 are large fruit Cibaxin categories bred by Professor Huang Quan and other experts from the Chinese Academy of Forestry Sciences. Compared to hyperparameters subspecies synthesis, the fruit of 状元黄 and 深秋红 are larger in size. This briefly is the two highest. This acerbic more similar to fruit flavor and easier to process. The fruits of 状元黄 and 深秋红 have been developed into a variety of products, including juice, puree, jam, freeze-dried powder, oil capsule, oil, vinegar, etc. Both 状元黄 and 深秋红 have been planted widely in Xinjiang. The production area increased approximately 24,000 hectares up to 2021. Studies have shown that the main nutritional and antioxidant content varies considerably among Cibaxin categories. Furthermore, the in vitro antioxidant activities of different categories of Cibaxin fruit varied considerably. The aims of this study are to determine the type and the contents of soluble sugars, organic acids, phenolics, VE, evaluate in vitro and cellular antioxidant capacity of 状元黄 and 深秋红. Part 2. Material and methods. 状元黄 and 深秋红 fruit were harvested in August 2021 from Qinghe County, Atil, Xinjiang, China. In our research, the soluble sugars, organic acid, phenols, VE, and carotenoid content of the two categories was compared by HPLC. Moreover, the antioxidant activities of two categories were compared and analyzed with DPPH, EBTS, superoxide annual scavenging capacity, FREP, and chemical to cellular antioxidant capacity as the activity index. Part 3. Result. First, soluble sugars. As shown in the figure, the total sugar, glucose, and fructose content of 深秋红 was slightly higher than 状元黄, but lower sucrose content compared to 状元黄, and there was no significant difference between the two categories. Glucose, fructose, and sucrose were the soluble sugars in Cibaxin fruit, of which glucose, fructose, and account for more than 19% of the total sugar. Second, organic acid. As shown in the figure, the total acids, malic acid, tartaric acid, citric acid, and succinic acid content of 状元黄 was significantly higher than that observed 深秋红, but hyaluronic acid content compared to 状元黄. However, there was no significant difference in shikimic acid content between two categories. Malic acid and cholic acid were the main organic acid in cibaxin fruit, which account for more than 19% of total organic acid content. Third, phenolics. Phenolics and flavonoids were important active components in cibaxin fruit, which often exist in free and bound states. As shown in the figure, the content of total phenolics, free phenolics, bound phenolics, total flavonoids, free flavonoids, and bound flavonoids in 状元黄 were significantly higher than those in 深秋红, and free phenolics and free flavonoids were considerably higher than those in bound states. A total of 12 free phenolics were detected in 状元黄 and 深秋红, including benzoic acid derivatives, flavonoids, and phenolic acids. Among them, both categories had the highest flavonoids content, followed by phenolic acids and flavonoids, with the lowest content of benzoic acid derivatives. The content of azithromycin and quercetin was significantly higher in 状元黄 than in 深秋红. While the content of prototypic acid, catechin, ferulic acid, and picomeric acid were considerably higher in 深秋红 than those in 状元黄. Phenylpropene metabolism was the only one to synthesize phenolics in cibaxin fruit. The content of phenylalanine, the initial substrate of phenylpropene metabolism, was an important reason for the difference in the content of phenolics. Therefore, we speculate that the higher content of phenolics and flavonoids in 状元黄 may be related to its higher content of phenylalanine and stronger metabolic activity of phenylpropene. Fourth, VC and VE. VC and VE were important vitamins in cibaxin fruit. As shown in the figure, VC content of 状元黄 was higher than that in 深秋红. Total VE, gamma VE, and alpha VE content of 状元黄 were higher than those in 深秋红, respectively. 状元黄contained a trace amount of delta VE. Alpha VE account for 93.34% and 95.15% of total VE content in 状元黄 and 深秋红 respectively. So alpha VE was the main VE in cibaxin fruit. Fifth, carotenoids. Carotenoids are the main pigment of cibaxin fruit. As shown in the figure, total carotenoids and beta-carotene content in 状元黄 were higher than those in 深秋红, and it contained more lectin. The lutein and zeaxanthin of 深秋红 were higher than those in 状元黄, respectively, and 深秋红contained a trace amount of beta-cytoxanthin. Sixth, antioxidant activity. DPPH, ABTS, superoxide annual, and FRAP free radicals scattering capacity were common indicators for evaluation the in vitro antioxidant capacity of active ingredients. As shown in the figure, the fruit of the two categories showed good in vitro antioxidant activities. The schematic capacity of APTS free radicals was the strongest, followed by FRAP, DPPH, and superoxide iron. DPPH and FRAP of 状元黄 were higher than those in 深秋红, and there was no significantly higher in schematic capacity of ABTS and superoxide iron. A large number of studies have shown that the antioxidant activity of cibaxin is closely related to phenols, flavonoids, vitamins, and characteristics. Therefore, the strong antioxidant activity of 状元黄 in vitro might be attributed to the high content of phenolic VE, VC, and carotenoids. 7th, cell cytotoxicity and cellular antioxidant activity. When mirroring the antioxidant activity of cells, it is first necessary to assess the cytotoxicity of the tested ingredients to the cells. The result of this study revealed that cell survival was higher than 98% when treated at a concentration of 21.25 to 2000 microgram per millimeter. The result indicated that the two categories had no toxicity to CACO2 cells in this concentration range. The determining condition of CEE value was similar to the physiological conditions in vitro and partly reflect the characteristics of absorption and metabolism of antioxidants, and the results have higher biological correlation. As shown in the figure, the CEE value of 状元黄 was significantly higher than that in 深秋红. In addition, no PBS cleaning showed stronger antioxidant activity than PBS cleaning, which might be due to the fact that VE and carotenoids in cibaxin are only loosely bound to membrane, and PBS cleaning is easy to remove. Therefore, the higher CEE value of 状元黄 might be related to its high content of phenolics, flavonoids, VC, VE, and carotenoids. Part 4, Conclusion and Perspective. The total sugar, glucose, fructose, and sucrose content of 状元黄 and 深秋红 cibaxin fruit are basically the same. The organic acids, phenols, VC, VE, and carotenoids content of 状元黄 are considerably higher than those in 深秋红. Both categories emerge excellent antioxidant activities in vitro and cellular antioxidant capacity, and 状元黄has strong activities. As 状元黄fruit is rich in organic acid and has excellent antioxidant activity, it can be divided into cibaxin puree and can also be used to extract bioactive components. Finally, acknowledgements. I would like to thank Mrs. Su, Professor Wei, Professor Jiang, and Professor Biyang for the constant support and encouragement. This work was financially supported by project of National Special Program for International scientific and technological cooperation. Okay, this has been my pleasure to give you my presentation. Thank you for your kind attention. Thank you.
Thank you very much for nice and interesting presentation. And for questions, I see in chat, and Axel would like to ask, what is the genetically base of the cultivars, crossing of subspecies or varieties? And similar question comes from Virendra, are hybrid with Russian Seabuckthorn? What is this genetically base of your cultivars?
I can answer these questions
Okay.
for her. And we use the two cultivars from the mother is from the hybridized from the Hipporamnois subspecies sinensis. It's a wild subspecies in China, and the father and is hybridated with a big species from Russia. Its name is fructose hippo. It's very is larger, and the wild species is small. So these two species were hybrided to make these two kinds of cultivar.
Okay, thank you.
Yeah.
And next question from Axel. This 24,000 hectares in Xinjiang, what is the relation between both of these cultivars?
What was the
relation? What is the relation between of both of your cultivars?
Yeah, they from the similar they hybridated from the similar two species, and until now we didn't know the exact difference between these two cultivars. The exact name of the hybrided father and mother we can't we are not clear that. Yeah.
Okay, then next question from chat from group Sava. Do you know the average volume of collection of Seabuckthorn berries in Xinjiang? What could be the average volumes of Seabuckthorn berries per year, I think?
Yeah.
How big amount of berries pick up per year? Maybe you know.
Yeah. It's planted in planted in a field the field, and have people to cultivate them and water them. So it's not wild. Yeah.
Yes, but amount of berries per year, how many tons?
Yeah, how many tons?
Do you know?
Yeah, I'm not sure how many tons.
Yeah, maybe maybe it's a better way to send these data after conference, because I think this question what Axel asked also not completely clear. He mean how many hectares are from the one and how many hectares are from the other variety. Maybe she can be so kind to collect the data and we send them later around.
Yes, yeah, it's true. Yeah. Okay, and you have question, Thomas, yes?
Yes, my question was only you mentioned that you use washing with phosphate buffer. The last picture what you show, or one of the last. And why are you washing the berries with a sodium phosphate buffer? What is the idea?
Sorry, it's a kind of method. Generally we use chemical methods to test the antioxidant activity, such as the scavenging of ABTS, DPPH. But this chemical method could not evaluate the antioxidant performance of test samples in physiological conditions. So we use the cells. We use in this experiment we use the CACO2 cells. It's a kind of cell from the human intestinal. This kind of cell could better to evaluate the antioxidant activity. So we use these cells to evaluate the antioxidant activity. But in this method, we use two kinds of different treatments. One treatment we in the experiment, after we treatment with the cells after we treatment the cells with our extract from Sebaxin, we didn't wash it with we didn't wash the cells with PBS, and we test it. So in this method, we test the antioxidant of compounds which associated with the cells and entered into the cells. Two kinds of substance. Some kinds are associated with the cell membranes, another entered into the cells. But when we washed the cells after treatment, the cells with the extract from Sebaxin, then we washed it with PBS. Then finally we test the antioxidant activities. In this experiment, we use the PBS to wash the cells because it could remove substances that only loosely bound with the cell membrane. So in this experiment, we only test the antioxidant activities of substances that entered into the cells. So this
I understand.
Yeah.
Now I understand. Thank you very much.
Thank you.
Thank you. More questions? I don't see Dan. Dan, thank you for all presenters, and I would like to ask for summary. Andrejs Brūvelis, head of Sibakton Association in Latvia. Welcome.